Welcome to today's SCA webinar with Bradford Prather on Deepwater Systems Classification and Sediment Partitioning. Before we start today's webinar, we'd like to ask a few questions about the demographics of the audience. So I'm going to launch a couple of polling questions. And the first poll is, what's your primary discipline? We're starting to receive responses now. Looks like we have quite a few geoscientists in the audience. Okay, most of you have voted, so I'll go ahead and close and share the results. 92% geoscience, 4% petroleum engineer, and 4% petrophysics. So let's go to the next polling questions. How many years of full-time experience do you have in the upstream oil and gas industry? Okay, we've got more of a spread in this question. Fairly representative sample. Most of you have voted, so I'll go ahead and share the results. 7% less than a year, 25% 1 to 10 years, 29% 11 to 20 years, 21% 21 to 30 years, and 18% over 30 years. So some in each area. So the poll should be closed now. And I'd like to remind the audience that you are muted, but you can ask questions during the Go to Webinar question feature. We will cover the Q&A at the end of the presentation, and you will be anonymous. And I'm going to share some slides here. Okay, so this is the webinar on Deepwater Systems and Classification and Sediment Partitioning. And today's presentation will begin shortly. Our speaker is Brad Prather. Brad received his BS from University of Kansas and his MS in Earth Science from University of New Orleans. And he worked at Shell. He worked in several different exploration plays around the world. And after he retired from Shell, he joined the University of Kansas and taught a number of courses there. Brad is chairman-elect for the Executive Committee on Geology Associates Advisory Board to the Department of Geology at the University of Kansas, and he has won a number of awards from APG. So the class that Brad teaches is the practice of seismic stratigraphy in deepwater settings. That is offered March 18 through 20 in Houston, Texas, in SCA's training center there. And you can see the description of the course, and you will get a taste of the course in the presentation today. So we have future webinars that are scheduled. In April, we have Shalim Shaker speaking on subsurface compartmentalization, hydrocarbon trapping, CO2 sequestration. Excuse me. In May, we have Bob Barbet, and he's speaking on reservoir and geomechanics is needed for a successful CCUS project. And in June, we have Rajan Shochki, and he'll be speaking about production data. We have some live online courses that are coming up. We have Dr. John Lee speaking on PRMS and SEC reserves and resource regulations in March. And in April, we have a well stimulation workshop that's taught by Dr. Leo Rodhart and Garrett Knitters. Other live online courses that are coming up include Christine Economides and Demetrius Hezignatou on carbon capture, utilization, storage from an engineering perspective. And then in June, we have Dr. Steve Sonnenberg, CCUS, a geological perspective. Of course, not only are classes taught in a public setting, but they can also be taught privately in your own location. And we also have several courses that are offered live online if you prefer the remote participation function. And of course, look to SCA not only for training, but for all your consulting needs in addition to recruitment of technical talent. And I will give the presentation rights to you, Brad. And you should be able to start your presentation.
Okay, thanks, Susan. So welcome, everyone. So we can just begin. So the question is, why classify slopes? And the answer is, you want to be able to take a facies map that you see there on the right. You want to be able to use maps like this to basically provide a depositional concept models for risking the presence of seal, source rock, and a reservoir. And you want to be able to integrate sedimentology so that as you describe the basis for your quantification of risk and uncertainty, you want to be able to add credibility to your explanation, because that's a way you judge whether an assembly of attributes or analog data that would use to construct a probability distribution, for example, that you use in volumetrics, whether it's reasonable or not. So that's the basic reason for doing that. It's to translate a seismic facies map in a quantification of risk and uncertainty. So as I mentioned a second ago, these conceptual basis for identifying analog data allows you to construct these probability distribution functions, and we're going to focus on reservoir today. But it also gives you access to reservoirs that have already been under production, allows you to benchmark reservoir simulations. And finally, if you work in a company that uses basin scale stratigraphic torque modeling to basically automate the mapping of gross depositional environments or environments of deposition, it allows you a way to test whether the models that are being produced are geologically reasonable or not. So what we're going to talk about today is the calibration of the slope systems from a very large data set consisting of more than 3,700 calibrated and seismic stratigraphic units, which are basically seismic facies, penetrated in 381 wells, representing 676 kilometers of logged section from 9 different basins. These data are augmented by about 7,000 sand picks and 2,000 more, about 1,200 sidewall samples. And you can find basically this database is too cumbersome to really access or use in a discussion like we're having today. But you can find a distillation of some of the key observations I'm going to talk about today in this paper published back in 2017. In addition to the analog data set for seismic facies, we also have characterized shallow analog studies and outcrop analogs, all in a similar way to those described for the slopes. That allows you then to interrogate the literature or other databases where these are described and pull together assemblages of analogs that all are geologically related. And this would include reservoirs. So the data tables used for this analysis include about 450 outcrops, numerous shallow analogs, and several thousand producing reservoir analogs, you can see here. So as I mentioned, this is the data using the database is rather cumbersome. So we've developed an app that uses the stratigraphic successions inherent as observed in the database to build synthetic stratigraphy. The app makes up for deficiencies that result from calibration of the subsurface with wells, which is intrinsically uneven. So it makes the data accessible and is designed to create a continuum of outcomes from basically calibrated with the data from the database from a variety of slope systems, but the continuum outcomes allows you to represent systems that are not necessarily represented by the calibration databases. But to do this, one needs to learn the language of slope classification. And if you want to get access to this application, it's free, and there's the website where you can go to download it. So here's a quick list of the descriptive components of the slope classification scheme I'm going to talk about today. We're going to touch on only a few of them, but it gives you the variety of input variables and types of data that were collected to build a database. But the basic element of the database is the seismic facies unit. So this is an example of a seismic facies map. It happens to be from 2D data, but what is represented there are ribbons of different colors that represent different seismic facies types. And then a polygon is drawn around each of the seismic facies types. And you end up with a map that looks like this. And based on its geometry of the seismic facies, plus the cross-sectional geometry observed in the seismic, you can make some stab at interpreting the environment of deposition. So here's an example. I'll just go through an example of how these data are collected. This is an example from the Gulf of Mexico. It happens to be through the Auger Basin. And so this is a typical stratigraphic an interpretation from seismic, showing stratigraphic boundaries and facies types. These are then projected into the well, which is right here. And this is what it would look like as projected into the well. So basically, all the tops of all the stratigraphic surfaces are data-based, and then the units in between the surfaces are characterized for their seismic facies. Now, eventually, the seismic facies are reclassified for environment of deposition, just as we showed in the example before. So also included, so basically seismic facies is a loop set. And so shown on the right is a synthetic seismic trace created from that succession of sediments. And you can see the subdivisions of different types of mudstone and environments of deposition. So in addition to capturing the seismic facies, also lithologic data is incorporated. In this case, it shows the position of sidewall samples. So to define the gross sediment caliber, or the amount of sand within a seismic facies unit, first you define the gross loop set thickness. And so you can see the set of loops on the right. Then you simply identify the stratigraphic units, and we use, from there, we use typical, let me back up a sec. We use typical log rule or V-shale calibration and measurements to come up with the net to gross, the net of every sand member that you see within the seismic loop set. So at this point now, we can already make some observations. Since we classified seismic facies and we then assigned an environment of deposition to the seismic facies type, we can now look at the sand distribution as a function of environment of deposition. So these are several sand distributions within 5 different environments of deposition. So these are about the only environments of deposition that we'll continue to talk about for the rest of the lecture. You can see there the sample size is pretty robust. Also note that captured in there are examples of where this particular environment of deposition was penetrated, but there was no sand. And that's in percentage terms. So for apron, 17% of the penetrations out of 900 penetrations had no sand. And then the other environments of deposition, you can see there are clearly three environments of deposition which you'd like to target as a reservoir. And two, the hemipelagic wedge and the mass transport complex are clearly very mud prone. But with this sample size, now we can start to subdivide these large collections of data for other attributes that characterize a slope system. And the first we're going to look at is characterization of different types of slope profiles. So there are three types of slope profiles that we use to characterize slope systems, and they range from graded, which is basically a shelf slope break here, a rather smooth gradient on the slope down to the basin floor, a step slope, which has obviously steps across the slope profile, and one with ponded inner slope basins. This is more typical of the Pleistocene of the Gulf of Mexico, for example. We also want to classify the position of these environments for their position on the slope. So there is no really good definition for upper, middle, and lower slope, for example, in the literature. So I've sort of come up with my own. And the way you define it is that you identify the shelf slope break for the interval of time your calibration data comes from, and the basin floor, and you just divide it into three parts. So these would be how the different slopes, the positions on the slopes would be distributed on a graded slope, on an example of a step slope system, and within an above grade ponded system. So now we can look at, with that additional characterization, we can start looking at how sediments are being partitioned as a function of these different types of slope systems and in terms of their environments of deposition. And there are a couple of obvious trends. The most obvious one, I think, is that the hemipelagic wedge, which is a wedge of mud that basically starts at the shelf slope break and tapers into the basin. And as you go down the slope, also you see an increase in the percentage of mass transport complexes, and interesting, you can see an increase in the number of apron deposits. And since slope systems are generally bypass systems, you get a higher percentage of aprons down in the basin floor than you do on the slope. And you also see that you get a higher percentage of aprons, for example, in slopes that have topography, like ponded slopes and step slope systems. So it suggests to me that the data that we're using here to characterize the slope systems are to make geological sense. So it's useful then to continue on. We can also look at how sand and mud are partitioned as a function of the environment of deposition in these different types of slope systems. Again, you can see the hemipelagic wedge, it's predominantly mud. There are some sands that are recorded in it. And, but you can really see a difference between the amount of mud that you find in aprons between graded, ponded, and step systems. You notice that the amount of mud in ponded systems is higher, makes up a higher percentage of the apron environment of deposition than in the other two types of profiles. And that's because mud is also ponded in topographic lows on the slope, just as sand is, and it's done it at a higher efficiency, if you will, within ponded basins than it does on steps, and certainly more so than on graded slopes. One of the other characteristics, and as I'll make a point later, this is a really important one and something that we call gross sediment caliber. Back in 1994, Redding and Richards provided a classification scheme based on grain size, and it is qualitative. So they give you these three different types of classification, three different types of systems: sand-rich, mixed, and mud-rich. And the list describes the characteristics of them. So based on these characteristics, you can then determine or take a stab at whether you're dealing with a mixed sand-rich or mud-rich system. So initially, when we started working with these data, we used this scheme to be able to look at the differences, how significant they are between sand-rich and, say, mud-rich systems. And as we did this, we started to assemble a fairly large data set. And what we noticed was that things that were typically called sand-rich by the criteria from Reddick and Richards tend to be on the order of 25% sand overall in the entire system, and or greater than 25%. And in mud-rich systems, the overall sand content tends to be about 15% or less. So this table describes this overall sediment caliber calculation, and it's really basically a summation of the entire logged section where wells exist in the shelf. And if that interval is divided by the net sand, it gives you a net to gross for every segment. You do that for the slope, you do that for the basin floor, and in this way you can now come up with a quantitative subdivision of sand-rich, mud-rich, and mixed systems. And if you look at globally at many these would be second order mega sequences from a variety of basins around the world, this is how they would plot using these criteria. That is 15% between mud-rich and mixed, and 25% differentiates mixed from sand-rich. So now we can go back and look at what we can learn about depositional processes on slope systems by looking at where sands are in different types of systems. So mud-rich systems, not surprisingly perhaps, seems to be relatively lean on sand across the entire slope down to the basin floor. And sand-rich systems tend to be richer in sand across the entire profile and in the basin floor. Mixed systems show this interesting characteristic that there's increased sand content in the lower slope. And that's because most of the mixed systems that we encounter in the calibration data set are from slopes with topography. So you're seeing the effects of topography capturing sand in what would generally be a bypass setting in mixed systems. So sand caliber, this variable is important. So of the slope systems that are calibrated, the step slope has the most data. So we can look at the difference between mud-rich, mixed, and sand-rich within step slope systems. And again, we see this very consistent relationship is that as you have more sand, the net to gross, for example, of apron deposits increases from mud-rich to sand-rich systems. And so this is important, and it tells us that this variable needs to be defined explicitly when we go in to collect calibration data. So let's just go through an exercise of collecting calibration data. So here's an example from the stratigraphic simulator. And in this case, what we've described is a slope profile type and a position that's a step above grade. And it's the objective interval. I want to describe the mid slope. And I use a system net to gross of 25%, all sort of defined as I discussed earlier. And the products you get from that are realizations of a whole different stratigraphic succession through a variety of realizations of the stratigraphy. Basically, what happens is that this program is seeded with an initial sand position and a seismic or environment deposition, and then it stacks vertically for 500 kilometers of stratigraphy based on that initial seed. And you can see here, you can change that seed. And every time you change that seed, these would change. But this gives you realizations of what the stratigraphy could look like which is useful if you want to, communicate to someone how sands might be positioned and different environments of deposition might be positioned within a well, just based on statistical means. Also gives you a lot of data on individual sand parameters within, say, an interval that's defined not by stratigraphic unit, but by thickness. And finally, it gives you some distributions which basically describe the relative percentage of different environments of deposition in that position on the slope. And it gives you a variety of ways to describe the net to gross for a stratigraphic unit from, or seismic facies unit or environment of deposition for this particular type of slope. So let's just focus on the environment of deposition net to gross. So it's a conventional look at it here. You get 3 distribution functions. These are exceedance probability plots. P50, et cetera, are shown. And it produces results that are totally consistent with the calibration data that underlies them. We've gone through a lot of tests of this, and we can't find any place that it really fails to describe at least the uncertainty, for example, of net to gross. So this is an example of, again, I think it was 28% or 25% system scale net to gross or net sand for in the previous example. So here's what it would look like if we change the gross sediment caliber to 13%. You can see the P50 drops off considerably for each of the different environments of deposition. And if I push it up to 30% gross sediment caliber, then you see actually a 25% difference between the P50 between the mud-rich, the 13%, and the 30% net to gross for an apron. So I mean, getting this right is really important. 25% at the P50 makes a really big difference in how you would characterize the volume of any particular prospect, for example. And finally, I mentioned if one were to try to calibrate or understand or validate a stratigraphic model for a basin, this is an example of an Albion model from a passive margin. There are ways to extract from numerical models like this the relative percentage of the different environments of deposition shown here in colors. And so you can characterize the upper, mid, lower slope basin floor. You can extract the percentage of environments of deposition, and you can use the tool then to define what would be the expectation based on observations from this large database. And then you can compare it to the model and to maybe like previous publications. Like there's, for example, the publication I mentioned earlier, where we quantified the relative percentage of environments of deposition in different parts of the slope. And it tells me that the model needs some work because it doesn't really represent very well what we observe from the stratigraphic simulator from Go Explore or from this publication. It doesn't necessarily mean the model is wrong, but it begs for an explanation, that's for sure. Especially if you're going to use that model or use the outcome from the model, which would be maps of distributions of environments of deposition, just laid out with a numerical model as opposed to mapping them. And finally, if you had access to an outcrop database where also characterized in this similar way, you could judge, you'd be in a position to judge the suitability or the likelihood that any given static reservoir model, perhaps as shown here, which typically are overly smooth and overly layered, you can use the examples from outcrops to judge whether the architectures you see that are produced in the static model seem to be realistic or would be realistic, or what should they look like. And the best place to do that is actually to go look at outcrops. So here's an example. We're going to go this is just an interface to a database that contains a lot of observations from outcrops. And we want to look at examples where we could actually go into the field. So we're going to go to the United States. We're going to look for environments of deposition that are aprons, and we want to look at examples where there are lobes, because that's what we think is the reservoir architecture that we have in an appraisal project, or even during for static modeling for development purposes. So you run that search, and you come up with a number of outcrops you could go to, and there's one in the Delaware Mountains, Colleen Canyon, and you go, great, so let's go to Colleen Canyon. Well, let's either go there or search the literature for examples of the outcrops that we could see at Colleen Canyon. And it turns out that there are some references we can go to in the public domain that describe the reservoir architecture at Colleen Canyon. And so that's an example of an application of going to, and then you can, based on what you observe here in the field, you can start to build up, you go, these elements I observe in outcrops in the field, do they exist in my static reservoir model? Do I expect them to be in the static reservoir model? And which ones are actually important in constraining fluid flow? And finally, in terms of static reservoir modeling, when you go into the dynamic world, you want to be able to access production characteristics of reservoirs that are consistent with what you think you're finding in the subsurface. So a reservoir database characterized for environments of deposition using the similar terminology can yield a whole variety of depositional or analogs of reservoir types. So here's just the producing reservoirs that are observed, the relative percentage from these different types of slope systems. And again, you can see some systematic patterns, maybe not surprising, but there they are. You can see that 12 slope apron reservoirs are more common in graded and out-of-grade systems, mostly because the slope in those systems are bypassed. And as you go up into ponded systems, you see more what we call aprons, both perched and ponded aprons. Some terminology that is used sometimes to describe aprons, but I haven't gone over the details here. But it's not that complicated. And finally, with all that production data, you can validate reservoir models and be able to judge their suitability for making some very significant business decisions. So that's pretty much all I have. I guess we can take questions now.
Fantastic. Well, thanks for sharing your slides today. I want to remind the audience that you are muted, but you can ask questions using the GoToWebinar question feature, and you will be anonymous. And I want to let everyone know that after today's webinar, you will receive a link to the recording of the webinar, and you'll receive an evaluation form and a link to register for Brad's class on seismic stratigraphy in deep water settings. It's offered March 18 through 20 in SCA's Houston Training Center. And so let's talk about the slide where you were talking about the model doesn't really represent what you're seeing in Go to Explore and the case study you had from the paper. It was towards the end of your presentation. I'm sorry, I don't have a slide number.
Yeah, I have it.
Okay.
So am I still in presentation mode?
Yeah, we're seeing the Logan Canyon Depisode slide.
This one?
Yes. Yeah, so how would you improve the model if it's not really representing what you're seeing with Go to Explore?
Yeah, so the way that sediments are distributed within these models are controlled by a set of algorithms. So in this case, it's using a basic diffusion codes to distribute the different sediments within the model. Now, so that you can use these diffusion codes in different ways, and it will result in different realizations of how sediments are distributed within the model. So you can control that. So what you want to do is you want to be able to create models which make sense geologically. And once you have models that make sense geologically, they might be useful, then the products from them will be useful for representing the subsurface. Clearly, if the model does not seem representative or is not geological, you shouldn't be using the model. Otherwise, it will give you erroneous results. And so there's a whole science behind stratigraphic forward modeling that we certainly can't go into here, but it's about manipulating these algorithms that distribute sediment, basically, digital sediment in space.
So it would seem like this would augment a lot of companies that maintain analog databases of all their producing assets around the world. If you could use this tool to help you find a better analog in some of the emerging exploration plays.
That's correct. So it just takes using the terminology on whatever database you have. And what I'm trying to show with this presentation is that this way of describing slope systems produces consistent results that can be, that allows you to assemble a set of analogs that are geologically related. And that's a good place to start.
That's great. You were showing on one of the slides that you changed the seed to get some different perspectives. Can you tell us more about that? I realize these are static slides, but what happens when you change that radio dial for seed?
So all you do is basically what it does is to begin with, to start the simulation, it randomly selects a environment deposition and a sand. And then based on the successions observed in the real world, it builds up a synthetic stratigraphy. So if you change the seed, it picks a different beginning sand and a different beginning environment deposition, and it runs the simulation again. So every time you change the seed, you get a different realization. So for example, here's a kilometer of section, and every time you change the seed, you'll see that this would change. And by the way, as you change the system net to gross, you would also see the content of sand change. And in real life, you can actually sit here and watch this panel right here. It scrolls through the entire 500 kilometers of simulated stratigraphy. It's more useful to maybe go to the next panel in this application, which gives you realizations from the 500 kilometers of the P90, which would be the most sand-rich part of the simulation. And for example, the P1, the P50 realization are intervals from the 500 kilometers of section. So it gives you a quicker way of assessing, what the range of stratigraphy might actually be. That's the point of having this, and being able to communicate, particularly to drillers. We found it most useful communicating with drilling engineers, setting some expectation of how many sands they might encounter in a particular interval, because most of this is happening below seismic resolution. I mean, especially if you're drilling wells below salt and the seismic frequency is about 15% or 15 hertz. As long as you fill in that white space within a seismic loop.
So if you're starting a new exploration project, how would you use the GeoExplorer as no or very basic screening tool, and later when you get extra data where you could refine your assessment?
Well, what you would do is you would focus on the key variables that help you define how this particular tool works. And that is work to define the system net to gross, and that's to measure or find data that supports an understanding of what the percent sand is on the shelf, the slope, and the basin floor. Then it is to work out what kind of profile type you have. And there are a variety of ways of mapping seismic facies that kind of give you what kind of profile type you are. Also, these different profile types are usually linked to the presence of mobile substrate beneath the slope, like salt or shale. And then try to work out the regional geology to find where this interval of interest you might have, where's the position on the slope. And through this particular study that we did that was published in 2017, we looked at all these variables to look at, among others, and these are the three most important. So these would be the way to focus initially on sort of coming to some idea about early on even, if I had a slope like this is the kind of sand content I should expect and where I should expect it.
So as some of our deep water prospects are getting into more the range of what we might call unconventional reservoirs, how would this tool help one to assess those that are on perhaps the verge of not being commercial?
So the question would be, what's the reason for non-commerciality? Is it reservoir quality in this example?
Right.
Yeah, so reservoir quality, I mean, that has to do with porosity and permeability, right? So that usually porosity and permeability are not defined based on stratigraphy. It usually has to, especially for deep water systems, because it's defined based on grain size that's available and deposited for deposition in the sand. So you usually go to different sources of information to come up with what kind of grain size would you expect in a particular region. This just tells you how the sands are distributed. I would use a different means to understand porosity and permeability distributions, different data.
And you mentioned the challenge of working in the subsalt. Can you talk more about that?
Well, so you get a poor image beneath the salt. You often don't see. So a lot of our understanding about how these slope systems work come from shallow analogs, at least in my experience. And you see beautiful images of what depositional systems look like, and that helps you define what the environments of deposition might be. But of course, when you go below salt, you don't get those kind of images. And the shallow images are based on higher frequency seismic because they're near the seabed. And of course, down to 27,000 feet, it's good if you can get 15 hertz, which means a single seismic loop could be hundreds of meters thick. And you have no idea there's no data there to inform you about what to expect within that loop, except for analogs. And if you have nearby analogs, that's great. If you don't, you're going to have to come up with some other means, and this could be a potential tool to help you come up with realizations of what you might expect to find within a thick seismic loop like you see below the salt.
And likewise, when you're in the more mud-prone areas, what are the challenges you might encounter?
Well, I guess depending on, you mean below salt or anywhere?
No, if anywhere.
Well, so the muddier the system, the less widely distributed are the sands. So, I mean, you have to find images to pinpoint a particular type of reservoir. Well, that's what we do anyway, honestly. But so the challenge for mud-rich systems actually is, do you want to be in there? Do you want to explore a mud-rich system? And clearly there are places in the world where you can, but you have to know you have to be aware in advance of what you might expect to find there. And you go, given these expectations, would this be, and in terms of probability of reservoir, net to gross distribution, stacking patterns, all that, is this a place that that would be good for business?
So does this change the way you approach seismic stratigraphy in general?
Well, there's many schools of seismic stratigraphy, so it depends. What we tried to do is focus on the least contentious descriptions of seismic stratigraphy, which is just basically a description of a seismic facies in terms of its map pattern and in terms of its cross-sectional geometry, or the loop district or the distribution of seismic events within a seismic facies unit. And then you map it out. And then based on the map pattern, you can interpret environment deposition, as opposed to getting into arguments whether this is a low stand systems tract or prograding wedge or channel levee complex or one of those things. So we try to take it down to the just most basic description of seismic facies units. So that's the focus is on the seismic facies unit and its interpretation in terms of environment of deposition.
So you focused today on deep water systems classification. Could this be used in other types of hydrocarbon systems?
Oh, for sure. But the issue here is that do these other systems have this database to back them up? So you can quantify like the sand content, sand stacking patterns and things like that, or grainstone thickness. The overall conceptual basis for how this work was done would work in any system. It's just a matter of the arduous task of collecting all of the analog data that would be needed to back it up, to make
Right.
to quantify things. It's a lot of work.
So would not source of sediment material define your lithology in the system? And how much variability do you expect within the slope deposition based on what kind of sediments get dumped into the basin?
So, right. So by that, I assume there are two things in most of these deep water slope systems that we're describing here are siliciclastic. So they're sort of binary. You have mud and you have sand. And so and that's the point of the gross sediment caliber variable, is to quantify the amount of sand and mud that's coming into the basin. And based on the topography of the slope, the depositional processes as turbidity currents flow down the slope, they encounter topography and they actually act, the slope topography acts to partition sand and mud in different percentages in different places. So this does, in fact, link entirely to the content of sediment, the percentage of sand and mud that encounters the upper slope. As we were talking about before with respect to sand quality, I mean, that's also an important attribute. If you don't have coarse grained sand at the shelf slope break, you're not going to have coarse grained sand on the basin floor. So that's really important too, but it's particularly important for, obviously, for porosity permeability characteristics, which this way of system doesn't really look at. We could look at if there are variables in terms of environment deposition, porosity, and distribution, but what you'll find is that it's more related to the grain size of the sand that comes into the basin, not necessarily the environment deposition.
Interesting. So I'll give our audience one more chance to submit questions and remind them that later today you'll receive a link to the recording of today's webinar, an evaluation form, and a link to register for Brad's class on seismic stratigraphy in deep water settings. That's offered March 18th through 20th in SCA's Houston Training Center. But of course, you could call us to set it up to be offered in-house if that's your preference. So thanks for joining us today. We really appreciate your questions and thanks for your interest. Goodbye.
Okay.